So in this video I will be solving part 2 of homework 2 here, where we are tasked to derive an expression relating the height of a ball in a rotometer to the volumetric flow rate. So I've made a diagram of the situation already, and here is the rotometer right here. You can see with the slanted walls of some height h, and with the ball inside of it. And that ball will have a diameter of d naught, and we know that because the diameter of d naught is the diameter of 0, so the ball will fill the rotometer at that height, so the diameter of the ball is d naught as well. And then we will have some flow rate q pushing that ball up through the rotometer. And we're going to call this point here point 2, and that will come into use later. So we're going to start off by making an equation for our flow rate Q. And we know that the flow rate is equal to the volume times area. And that's just for any flow rate. And in this situation, we're going to be calling it V2 and A2. And we have already calculated or derived an equation for V2 in class using our textbook. So I have that written up here, which we will input later when we are trying to derive our equation relating the height of the ball in the rotometer to the volumetric flow rate. So we already have V2, and now we are going to be trying to find an equation for A2. And we know that the area of a circle is pi d squared over 4. That's just an area for any circle using the diameter. And what we're going to be looking for is the difference in area from 0 to our point 2. So how we're going to do that is we're still going to have Q equals V2, and then it will be our difference in area, so just pi d squared over 4, and that d is the diameter at any given height, minus pi d naught squared, our diameter here, over 4. So now what we can think about is we're going to want to try to plug something in for d to get everything in terms of d naught. So we can actually make a linear equation in the form of y equals mx plus b, because these sides of our rotometer are actually straight lines with a slope that we're going to call m. So any diameter here, d, is going to be equal to our starting diameter, d naught, plus that slope times our height that we are at, the change in height. So now what we can do is square both sides of this equation, because again our end goal is to plug this in for d squared here. So square this and square this whole side, and we'll end up with d squared equals d naught squared plus 2 d naught m h plus m squared h squared. So now all we have to do is plug this in, and I'm going to do that up here. So if we are combining like terms, we will end up with pi v2 over 4 times, and our d naught here is going to cancel with that d naught, so we will end up with two d naught m h plus m squared h squared. And that will still equal q. So now we just input our v2 equation, which we have up here. So we'll have q equals pi over 4, and then our v2 equation here and then for this right here, we need to keep in mind that our m right here is our slope of the rotometer, which will actually be a really small number. So that really small number squared is basically just going to be 0. So we can get rid of this whole portion of the equation right here, because m squared is 0. So we'll end up over here with 2 d naught mh. And then you can notice that we can bring this 2 over here, and we will end up with just pi over 2. And then again, our v2 equation. And d naught mh. And in most rotometers, this v2 equation here is just labeled by b, which we will call a constant of proportionality. And on most rotometers, that constant of proportionality is given. So this will actually end up being our final equation relating the height of a ball in a rotometer to the volumetric flow rate in a rotometer.